come into the categories of lepton, and lepton is like a photon, an electron, and a quark. So these are the things that cannot be divided into something else. And a baryon, like a neutron, can be divided into into parts, and those are called the quarks. So, and proton is not an fundamental particle. The quarks that made make up the proton are fundamental particles.
Okay, so a photon is one of them, the fundamental particles.
Ye- Yes. Some.
So they have mass.
No, they don't. कोई मैसेज है Wait, कहाँ से check? Information chat, are they almost same like protons? uh, Sir, I did not understand what were you trying to say, like what are same like protons?
Well, the logic that you gave for which the uh, particles are going with mass irrespective of a perfect universe, I mean the symmetry that doesn't follow in our universe, isn't that the same case with photons? And the photons should have the mass as well.
Okay, so
The interaction that you just talked about, what was that?
so the interaction. Okay, so I think so you got something mixed up. So if a quark moves at light speed, like it moves if it moves like at light speed and does not get interacted with the anti-quark and other things, uh, then it would have a zero mass. But in our universe, it is moving through a sea of like made up of thick honey, because it is getting interacted with the anti-quark and other things. It is getting slowed down, and then it stores that slowed down mass and energy into mass. That trapped energy is the mass that we have of the quark. And in photons, it is a completely different case. uh, it does not follow. So like the chiral symmetry that I just mentioned to you was for the strong nuclear force. It was not for the you can say the photons, I think so. uh, I uh, forgot the case for photons, but the chiral symmetry was for the strong nuclear force.
Well, it should be for any particle, right? Because the universe is the same, the medium is the same, the vacuum is the same.
Okay, so uh, no, like the chiral symmetry. Okay, so let me explain what the chiral symmetry is. So, like, has the universe cooled down after the Big Bang? What happened that the energy of the strong force condensed, and instead of an empty space, the vacuum became a chiral condensate. So it is a dense, invisible sea of quarks, anti-quark pairs. In a perfect world, the vacuum would be empty, but in our universe, the strong force is so powerful that it is actually more energy efficient for the vacuum, and that's why it is filled with a thick soup of particles. So it means and it also means that our universe is metastable. And if our vacuum is metastable, then there is a very uh, tiny chance that a bubble of lower energy vacuum could form. So this was the earlier later part of the presentation I was trying gonna explain, but I explained it right now. So it is because of the chiral condensate it's happening. So did you get me?
See, I got you in that part, but what I'm trying to ask is if you are trying to mention an ocean and a thick honey, that means that each and every particle that goes through that water has to mandatorily interact with the drag. Isn't that the case?
Okay, so the thick honey case, like I only said for the quarks. So it's like if you're going to move through a sea that is made up of thick honey, you will
Yeah.
be slowed down. And in the case of quarks, what happens that as it slows down, it stores a massive amount of interaction energy, has mass.
Yeah, I understood that case, but you cannot say that the drag is just upon us and not on the dolphins. I mean, each and everything that goes through the ocean has to go through the drag. And if
Okay.
it doesn't follow the aerodynamics, it would go through more drag. And if follows it, then it would be reduced. So
I
you cannot
understand
say
you.
that photons do not interact at all. They should be, right? That is
Yes.
the logical point. That is the intuitive point.
So, what? So the C. Let me talk about the C that I was trying to say is the chiral condensate. So it is a sea of antiquarks and quark pairs. So that is the C that I was trying to say. And if the chiral condensate was not there, it would be like moving in air instead of thick honey. And the photons do not interact with the quarks and other stuff. So this is for the strong nuclear force only, the quarks and gluon pairs.
Oh, because the photons are not made of quarks, so that
Yes.
they are not interacting with them.
Yes. So
Okay.
the yes. So the chiral condensate is the ocean that I was talking about.
Okay, and you are saying that those are responsible for mass, but just in
Yes.
quarks and not all the stuffs.
Yes.
Are you aware of
Lattice. Yes.
the Higgs boson and boson field?
Yes. Yes. So those are the things that are responsible for giving mass to them, the particles, and those are the reasons because our universe is in a metastable state. So this is the later part of our presentation. We'll talk about
How do you connect these two? I mean,
what
boson field and this field that you just talked about, are they not the same thing?
boson field and
And the thick honey thing that you said was responsible for giving mass to quarks.
okay. So a chiral. So the thick honey is the chiral condensate,
Yeah.
and a Higgs particle. I uh, so I did not understand the question very well. So I think so. We should discuss it later, and we should get to the presentation part. We'll
Okay.
discuss it later. And there are some questions in the chat. So someone is asking. So photons are same as protons. So and photon is a fundamental particle, and a proton can be divided into parts which are called quarks, and the quarks cannot be divided into any further parts. So that means the quarks is a elementary particle that makes up the photons, the protons. What is Higgs particle? Bosons are identical and indistinguishable, I think. Bosons are identical. So a boson. So a boson is a force carrier, and a meson is also an boson, but it is not a force carrier. And new people have joined. Syed, Frederick, Praveen, and Cosmic Buzz have also joined. So thank you for joining us. So I think so. We should get to the presentation. Lattice QCD. So it is a numerical approach to solving quantum chromodynamics by discretizing space-time. It allows for non-perturbative calculations of hadron properties. Advances in computational power have significantly improved the precision of lattice results. So So in this, what happens that scientists turn space-time into a 3D grid that is called the lattice. They put quarks on the corners and gluons on the line. They use the world's most powerful supercomputers to simulate the buzzing and swirling we talked about. And like in uh, someone has a question. So Saksham has a question. What is the question?
Aryan, I did not understand lattice very well.
Okay. So lattice, what is it? So it is in 3D grid that scientists have made. So they put quarks on the corners and gluons on the line, and they use very powerful supercomputers to stimulate the buzzing and swirling of them. And then they divide it. So like for instead of the entire universe, we take a tiny box of space and time and divide it into a grid. So like quarks are placed on the corners and gluons are on the lines, and they use computers to stimulate that. So it is a non-perturbative theory. So like it cannot be solved by regular humans. We need to get many advanced technological stuff to make to make and solve these things. So did you get it?
Yes, Aryan.
Okay. Hadron structure. The internal structure of hadrons can be described by a pattern distribution functions. These functions give the probability of finding a quark or gluon carrying a certain momentum. Deep inelastic scattering experiments have been crucial for probing a hadron structure, mesons and baryons. So mesons are particles made up of quark and one antiquark. Baryons consist of three quarks bound together by the strong force. Both type of hadrons are described with quantum chromodynamics with their spectra studied experimentally. So a meson is made up of one quark and anti-quark. Like if we have one red quark and then we will pair it with an anti-red quark. And a baryon is made up of three quarks. It also uses the primary color rule. You take one green, one red, one green, and one blue quark. QCD. So these are explained by quantum chromodynamics. And for gluons, it is also the case. There are also it also follows the primary rule, color rule of the three, and it also has counterparts. So the special unitary group of uh, 3 degrees, it says that the colors of gluons is about 8. So and that is because like that is not 8 9 because of mathematics. It is the like let's say the perfect spot for our universe. Quantum chromodynamics in colliders. So QCD processes dominate many phenomena observed in high energy colliders. Jet information is a key signatures of quarks and gluons interaction. Precise QCD's calculations are essential for identifying new physics signals. So I have a question for everyone. So what are the differences between baryons and bosons? So does anyone know? Saksham, Aryan, and Satyajit.
Means you are asking the differences between baryons and bosons.
Yes. Do you know that?
So baryons are the composite subatomic particles made up of three valence quarks belonging to the hadron family and acting as a fermions with half integral spin. Whereas bosons, I think so, bosons are subatomic particles with an integral spin followed by Bose-Einstein statistics.
Okay. So like, can you give me an example of this? Like, how is that useful for us? Okay. I think so. Someone has some questions are there in the chat. So what is QCD? So QCD is this. So it stands for quantum chromodynamics, and baryons have large densities and bosons have small densities. So uh, you are right a little bit, but there's some partial error. So in the boson family, there are photons also, and their differences can be seen like if we have a laser. There are a lot of photons which belong from the boson family in them, and if and then they can be concentrated in many in a small place, but that is not the case with the baryons. They cannot occupy the same quantum state. So we can have a infinite number of boson particles in one small space. So what that is the main difference between them, and this can be seen in jets and lightsabers, where photons are concentrated in one place.
You
Okay,
can also say that fermions cannot share a quantum state, whereas a boson can share a quantum state.
okay. So Saksham, can you read this slide?
Okay. Spontaneous symmetry breaking. Chiral symmetry in QCD is spontaneously broken in the vacuum. This breaking generates masses for certain hadrons and affects pion properties. The phenomenon is a crucial aspect of understanding hadron mass generation.
So chiral symmetry in quantum chromodynamics is spontaneously broken in the vacuum. This breaking generates mass for certain hadrons and affect pion properties. The phenomena is a crucial aspect of understanding hadron and mass generation. So it is the reason particles like the pion exist, and why are they so light? Without this symmetry breaking, the strong force wouldn't behave as it is, and protons wouldn't have mass needed to form stable atoms. So it is the cosmic event that turned a soup of light fast particles into a heavy solid matter that makes up our body. So when a spontaneous symmetry breaks occurs, the vacuum, empty space inside a proton, changes its state. It becomes filled with condensate of quarks anti-quark pair. Think of it like moving through the air versus moving through thick honey. So, so ladies and gentlemen, do you have any questions? Okay. So I have a question for everyone. So why does this?
Aryan, I have a question that why is it is necessary that chiral symmetry in QCD would be always broken in a vacuum?
Okay, okay. So what were you trying to say, that the if this symmetry didn't break, it would have made the quarks have no mass, and this might be a case for some other universe where it follows this chiral symmetry, and this symmetry broke because uh, like if a quark traveled at the speed of light, as it should, because has the chiral symmetry tells us that. But what happened that as the universe cooled down after the big bang, the energy of the strong force condensed in instead of empty space. The vacuum became a chiral condensate, a dense invisible sea of quark and anti-quark pair. So in a perfect world, the vacuum would be empty. But our universe, the strong force is so powerful that it is actually more energy efficient for the vacuum to be filled with thick soup of particles. So what does that mean, and how does that signify that quarks have mass? So do you know why? So uh, if this symmetry broke, this chiral symmetry broke, so why did this give mass to the quarks? Do you know, Saksham?
Yes, Aryan, what is your question?
So, like, has this symmetry broke? So, why did this symmetry breaking give rise to quarks having mass?
I didn't you get your question means what are you trying to say?
So, like, how does this chiral symmetry breaking lead to quarks having mass? So, Satyajit, do you know why does that happen?
I think Aryan, it happens through spontaneous processes where minor random molecular or environmental fluctuations are amplified, forcing a system to adopt a specific asymmetrical state.
Okay, so like, can you explain that in simple words? Okay, so I think so,
I think
Satyajit. Yes, yes, Saksham. So, so Saksham, what were you trying to say?
no, Aryan, nothing.
Okay, so I think so, Satyajit, you were trying to answer and say something. Satyajit.
The breaking of this symmetry, as you said, results in the formation of quark condensate in the vacuum.
Yes. So how does that
And
give rise to mass? Yes.
so, as you mentioned, going through that gives a drag, and that drag accumulates to form mass. That energy, that extra energy, gets in the form of mass in the quarks.
Yes. So like, what happens in the interior of that proton? So can you explain that one?
No.
Okay. So in the interior of the proton, this also happens because the quark is getting repeatedly absorbed and reconstructed. Its speed significantly drops, and because the quarks are now struggling against it, they slow down very much and store a massive amount of this energy has has mass. So that is how quarks have mass, and this is how breaking of this symmetry led to particles having uh, quarks having mass. So Sayed has also joined. So thank you, Sayed, for joining us. If you have any questions, you can ask us. Fermion. So Satyajit, you have raised your hand.
Which speed are you talking about exactly that is slowing down here? Is it the case that every particle is going through the speed of light?
So like I was talking about the quarks. So if they had followed the chiral symmetry, so there's one more a significant part of this. It is about left-handedness and right-handedness. So if they would have followed the chiral symmetry, they would have moved at light speed because they do not have any mass. But as they can interact with their counterparts, which means that they are getting slowed down. So it is like they are struggling against the drag of the vacuum now, and that is because of the chiral condensate. And as they slow down, they store this energy into mass. So that's that is the answer. Okay. So yeah, did you get it, Satyajit?
So what you are saying basically is that the natural stage of every massless particle is moving with the
Yes.
speed of light.
Yes.
Then what defines which particle gets how much mass? Like not every particle are of same mass. Some interact more, some interact less. What
Yes.
defines it?
So I think so. Like quarks, I think so. If it's about how much an particle interacts with that chiral condensate, and if it interacts more and gets slowed down more, it would have more mass. So I think so. That's the case.
But at the same time, each and every proton in the universe has the same mass, and that of electron are different.
Okay.
So,
So
of one species, every particle is of the same mass.
yes.
And
So
you must be aware that the protons and neutrons, of which are assumed to have the same mass, are not exactly the same mass.
okay. So uh, so some so uh, this leads back to the quantum fluctuation part. So where the quarks are getting in and out of existence, and so that is one of the main reasons for this chiral condensate, the dense invisible sea of uh, quarks and anti-quark pairs. So like what happens that the conservations is always happening. Like if it borrows the energy from the vacuum to create new quarks, that quark will also go go and disappear in and out of existence because it had borrowed the energy from the vacuum. And if we take any specific instance of time, what would happen that there would be a conservation, like the half would be quarks and the half would be anti-quarks. So that will just leave the three main valence quarks. So that's the case, and that's how they are getting energy. So uh, this has to do things with quantum fluctuations, the uncertainty principle, and many other quantum phenomena. So, so did you get it?
Yeah, I get what you said, but again, if you talked about annihilation, then how would you justify the formation of three valence quarks anyways at the
Annihilate.
end?
Okay, so they were getting popped in and out of existence. So like it is an invisible sea of quark and anti-quark pairs. So they exist for a instance in space and time, and they interact with that, and then the that annihilation in that annihilation, what happens that it gets reconstructed into that quark, and with this different colors because it interacted with an anti-quark. So that's happening. So it's an instant process, it happens at very fast pace. So did you get me?
Yeah, but I'm not sure if that answered my question. What are
Okay,
valence quarks again?
I think so your doubt is in the particles, like the invisible sea of quark and anti-quark pairs. So uh, to understand this, we can go at the edge of a black hole. And what is happening at the edge of the black hole is that the virtual particles are getting created. And what happens if it happens to be at the exact at this a sweet spot, what can happen that the virtual particle can come into reality, and its half counterpart would fall into the black hole and the other half will escape to reality. So it means that the virtual particle is getting alive for a moment.
Okay, okay. I guess now I got my answer.
So it is pretty tricky, right?
Yeah, yeah.
Topological aspects of quantum chromodynamics. So quantum chromodynamics has rich topological structures such as those influencing the vacuum. These structures make contribute to the mass of the mesons. Topology plays a role in understanding the non-perturbative vacuum properties. Experimental tests of quantum chromodynamics. So let's talk about the topological aspects of quantum chromodynamics. So they are the physical reason for the chiral symmetry breaking, the thick soup uh, of vacuum that we have talked about. Without these topological tunnels, quarks wouldn't have the mass needed to form us. So that is the reason that we are here right now. Experimental tests of quantum chromodynamics. So particle accelerators like the LHC and Tevatron tests quantum chromodynamics predictions through collision data. Measurements of cross sections and jet properties verify the theory's accuracy. The same accuracy and can point to physics beyond the standard model. So the picture given, it gives the proof that why there are eight colors of gluons. And why not three? Because SU3 means super unit, special unitary group of 3 degrees. So it should have had nine, but it is only eight because it is the like the sweet spot for our universe to exist at. So there was a test conducted in 1979 at the Petra Collider. They saw something very they saw something incredibly normal. When you smash an electron and a positron, the common sense says that we should get two jets of particles, one for a quark and one for an anti-quark. The third jet, but there was three jets, and the third jet was the first direct proof of a gluon being kicked out of the collision, and it matched the math perfectly. So, some challenges in quantum chromodynamics. Non-perturbative effects make calculation complex at low energies. Developing high effective models and computational technologies remain an ongoing effort. So now we are going to talk about chiral symmetry. The particle, there are two main types of particles: right-handed particles, the particles that spin in the same direction as it moves; left-handed particles, the particles spin in the opposite direction of its motion. And like if quarks had zero mass, they would have moved at the speed of light. In this state, a left-handed quark would stay left-handed forever, and a right-handed quark would stay right-handed forever. The universe would treat these two teams as completely independent and equal. This perfect balance is called the chiral symmetry, and our universe does not follow that this chiral symmetry because of, like you say, like we can say, it is because of the chiral condensate. So the vacuum has a medium. So the idea that vacuum is a space or honey especially is precisely how like physicists think about the chiral condensate. So uh, so like while the Higgs field gives quarks their seed mass, about 98% of the mass of a proton comes from drag and interaction energy of quarks moving through the chiral condensate. The chiral condensate, also known as the quark condensate, is the invisible sea of quarks and antiquarks that we've talked about that fill the every corner of our universe. So the formation of this condensate is the physical evidence that this chiral symmetry has been broken. So like it is the uh, so when this symmetry breaks and the condensate forms, it spits out some specific particles called the pions. So I think so. These are also from the boson family. So they get one quark and one anti-quark. So these are the bosons. So these like are the ripples in that invisible sea. Whenever the quark bumps into an anti-quark, it annihilates and gets recreated. And when this symmetry breaks and the condense forms, it spits out specific particles called pions. These are the bosons that repel in the invisible sea because the quark is constantly being reprocessed by the vacuum. It cannot zip the universe at the speed of light. It gets bogged down. The energy required to keep this swapping happening is trapped in the space in the quark. That trapped energy is exactly what we measure as the mass of it. In physics, we call this as a dressed quark. The quark is no longer a tiny liquid point. It is a fat particle surrounded by a chaotic cloud of these interactions. So in the if we had a universe that would have followed these chiral symmetry, we would have had naked quarks which could have roamed around in the universe. But that's not the case in our universe. So, did everyone get what was the saying, Saksham and Satyajit?
Are you? Aryan, can you explain chiral symmetry in simple terms?
So like chiral symmetry. So there are supposed to be two teams, the right-handed team and the left-handed team. So if the quarks have had zero mass, they would move at the speed of light, and at that pace they would not have interacted with something else, and it means the quark would not get reprocessed and reconstructed, which means that it would not be getting slowed down, and which means that it would have no mass. So in a universe that follows chiral symmetry, what would happen is that it would have had just no mass. There would be just no mass in it. So did you get what was I saying?
Yes, Aryan.
Okay. So Satyajit, did you understand what was I saying?
Yes.
Okay. So did you understand the pions concept, Satyajit?
Oh, yes. Yes.
Okay. Breaking chiral symmetry. So chiral symmetry treats left and right-handed quarks as independent weightless teams. In our cooling universe, the strong force made the vacuum thick with a soup of quark anti-quark pairs called a condensate. This soup forces quarks to flip their handedness as they move, creating drag. This drag is the mass that builds protons, neutrons, and eventually you. So, like this is like a more harsh toning, and it would be a little more difficult to understand. So that's why I made it simpler by saying that these interacted with each other and it got reconstructed. It means that it is changing teams uh, at any moment. So that creates the drag that we experience has an mass. So now we are getting uh, at the ending of our presentation, the metastable universe. So it is a cosmic state where a vacuum, the very fabric of space, is stable enough to last for billions of years, but it is not at the absolute lowest energy level. Or as of 2026, current measurements from the Large Hadron Collider continue to suggest that we may live in a false vacuum. So So Higgs field is the field that is like in a metastable state. It is not like there is one thing. There is one more thing concept called the Mexican hat. So like it says that as our universe was formed, it went to a lower state, and the like uh, on the edge, like it was first of all it was on the edge, and then it followed to the gap in between, which was the lowest point. But we what we think right now is that there's a peak, like we are on a mountain, and there's a one thing that there's a valley that is more deeper than this, and our universe can quantum tunnel through that, and that is that there can be some chances of this happening. So like it's a phase the universe is going through. So, and like our universe appears to be right on the edge between stable and metastable. So it like feels very strange. Think that the laws of physics are working like that. So it also means that the weight of a quark, the phase, it might be a phase that the weight of a quark might be a phase in our universe. So if that happens and if that thing just disappears, if we transition to a lower energy state, the most stable state, what will happen that there would be there would be a zone expanding at the speed of light, which will destroy anything that comes in a way and will rewrite things. Like it would be having like in a chiral symmetry breaking universe, there would be another universe that is following the chiral symmetry. So that means that in that universe that is expanding at the speed of light would have quarks that have no mass. So it means that as if so as soon as it touches us, we would just cease to exist. So like it is an existential crisis type of thing that we may like just disappear out of the world in any instant. So the chances of this happening are very high, like in very high, because we are at the at the at the sweet spot between stable and metastable. So what can happen is that in millions or trillions of years, we may transition to a lower state of energy, which is the most stable state. And if that happens, the it would create another universe inside it, which would be expanding at the speed of light, where chiral symmetry is getting followed and the quarks have no mass. Conclusion. So, quantum chromodynamics is a fundamental and complex part of modern physics. Ongoing research continues to deepen our understanding of the strong interactions. Quantum chromodynamics remains a vibrant field driving discoveries in particle physics and cosmology. So, like the top and calm quarks have been discovered through pure mathematics. Like so, we are done with our presentation. So, thank you for joining, everyone. And if you have any questions, you can ask us. So, Victor has also joined. So, thank you, Victor, for joining us. Hello, Victor. Okay, Victor. So, today our topic was about quantum chromodynamics. We discussed about we discussed deeply about how are these things, the quarks and gluons, getting interacted, and why do quarks have mass? And it is because our universe is not following the chiral symmetry, and that is the main reasons because we our universe is having mass, or the quarks mainly, we can say. So, any further questions, anyone? Okay. Okay, so you can try to join us next class on time. So thank you everyone for joining us. So any further questions? Would anyone? Okay. So Frederick, thank you everyone for joining us. So someone named as Frederick has been there for the whole presentation. So thank you, Frederick, for joining us. So thank you. So any further questions by anyone? Sayed, Frederick, Shaurya? Okay, I don't think so. There are any questions. So, hello, Sayed. Uh, Sayed, can you introduce yourself to me? Where have you joined from? Okay, okay, I think so. Okay, I think so. We should end up. Hello, Sayed, are you here? Sayed. So, Sayed, can you introduce yourself to me? Where have you joined from? Shaurya has also joined. So Shaurya and Sayed, can you introduce yourself? Hello, Sayed. Sayed, where have you joined from? Your voice is not coming.